please, over to you.
Okay, thank you very much. Thank you, Michael, for inviting me to present this seminar and also for a nice introduction. So most of this stuff that I will present was done in collaboration with my professor Tomáš Blažek and a student, PhD student, Viktor Zaviet. So this is a plan for this seminar. In the first part, I will briefly review mostly the textbook stuff, the imagining kinematics in Feynman diagrams, how they can lead together with some irreducible complex phases in couplings to CP asymmetries and unitary constraints. And the only there will be almost no new physics in this first part, but there will be a new way how to describe these calculations, how to perform them in a diagrammatic way. In the second part, I will jump to application of the CP asymmetric calculations in the Boltzmann equation, so the kinetic theory. And then there will be short example on Dirac leptogenesis from scattering. This is recent work with Julian Heek and Jan Heesik from Virginia and from Aachen. And then I will briefly comment on unitarity and how can we get some approximation of thermal corrections in this way. Okay, so let's start with the first part. So we have the usual and simple unitarity condition for zero temperature scattering metrics, as you learn at the first lecture of QFT. We can split it into the unity and interacting parts, which is represented by the T matrix, conventionally with the imaginary unit there. And we can compute, we can take the diagonal elements of this unitary condition, and we will get imaginary part of this T matrix from some initial state to itself. So this is mostly known as optical theorem in QFT, and each contribution to this imaginary part of the forward scattering transition matrix can be represented as a cut of a forward scattering diagram. So in general, we have some initial state with P particles from 1 to P, and we can draw all the possible diagrams of this type from initial state to itself at some order in perturbation theory, and then we can make all the possible on-shell cuts through those diagrams. And what is good to know is that for each cut line, we have to integrate over 3 momentum. The line is put on mass shell, and at one side of the cut, it does not matter which one, but it should be consistently done in all the contributions. So let's say to the right of the cut, we have to replace all the I epsilons in the propagators by minus I epsilon because of the Hermitian conjugation here. Note that we are reading these matrix elements from right to left, but diagrams are drawn from left to right. So it's just a convention how we read. Okay. I also occasionally use.
Can I ask one quick question? So on the slide before, so you had there that delta plus.
Delta plus is delta function times theta function k0. So only positive frequency part.
Okay, thanks.
This is a mathematical identity that you can add this delta function and integrate over zeros component, and you will get what you have on right hand side. And this is a Lorentz invariant measure we usually put here. Okay. So sometimes I integrate over the final state, and then I will use this notation that it is some not a matrix elements, but simply squared amplitude from I to F. Okay. Then we may ask, so the observation is that from unitarity we can see that having a forward scattering amplitude, it can develop an imaginary part in the kinematics. When I say kinematics, I mean everything except of couplings. So we can split the diagram into couplings and kinematics. These couplings may be gauge couplings or some Yukawas, which is the interesting case, because in Yukawa matrices you can have some irreducible complex phases, which will turn out to be important. So couplings and kinematics is a Feynman diagram. Okay, so the kinematics can develop imaginary part. What about the off-diagonal elements of these T matrices? And there are a few cases we can look at. So first, we will take the unitarity condition again and take non-diagonal elements of this condition, so some I and F states. So First case is when we have real couplings only. In that case, the T matrix is symmetric, because this can be easily seen from Lorentz invariance, because these T matrices can only depend on products of four momentum, and when you switch the sign of each four momentum, then the whole thing will be invariant under such operation. So this T matrix with real couplings is symmetric. And you can exchange these indices and again having imaginary part of some non-diagonal T. That again can be represented by a cut of a diagram from I to F. Another case, also interesting, is that we may have some non-real couplings, but we only look at the kinematics of the diagram. So we will write an amplitude from I to F state as a sum of the couplings and kinematics. There will be diagrams of different orders. The C matrices representing the group of couplings in each diagram is Hermitian. The kinematics, pure kinematics, is again symmetric, and we can look at the coefficients in this identity here, at the coefficients of certain order, and have many relations of this type. So each diagram we can have this optical like theorem. What is important to say that there is an exception from this, and it is the case of non-abelian gauge theories, where you have Faddeev-Popov ghosts, which contribute to imaginary part, and but they cannot be included in this sum. So in that case, it's a bit more tricky, because you cannot write this optical theorem diagram-wise. But the main point of this introduction is that when we have a diagram usually of higher order, it can develop imaginary part in kinematics. Okay, so how it is related to the CP asymmetric reactions? First, we assume the CPT symmetry. So the most standard theories like QED, standard model, all these theories are CPT symmetric. We do not include any exotic type of Lagrangians or what. And we define CP asymmetries as T asymmetries. So we will just switch the states. Then each of these contributions can be written usually as a sum of a tree and loop level part. We will separately treat the couplings and kinematics again. And when we write the difference of these squared amplitudes, we will get from the interference of tree and loop contributions, we will get that the CP asymmetry is proportional to a product of the imaginary part of the couplings and imaginary part of the kinematics. So usually you need both to get CP asymmetries. The only problem is, so we need to get a CP asymmetric reactions, which is a conditions, one of the Sakharov conditions for baryogenesis in the early universe. You need a theory in which you can develop loop kinematics with non-zero imaginary part, and the model has to come with irreducible complex phases in couplings. The question is if this is sufficient condition to get a CP violation in reaction rate, and it turns out that it is not. Why? Okay, so let's look again at the unitary condition written now in this form. We can cross this unity and linear part, and taking the diagonal elements of these quadratic terms, we can get the unity condition like this, and moving one sum to the other side, we will get the sum of the asymmetries over all the final states with a given initial state will vanish. Also, we can have sum of initial states with the fixed final states, and you will get the same, obviously. So this was known from the times of Dolgo and Kolb and Wolfram. There are several works on this CPT and unity constraints, because you assume CPT symmetry and you work with unitarity, and you will get this condition that the sum of the asymmetries vanishes. There is, for example, the work of Anson Hook from 2011 on how these CPT and unity constraints affect the freezing and baryogenesis. And also work by Jason Baldes, Caleb Petraki, and Professor Raymond Volkas on matter asymmetry generation from annihilations. where also it is a PRL paper, but you can, in the introduction, there is a detailed explanation how these CPT and unity constraints are manifest for the 2-to-2 reactions. Okay, so this is an important thing, but when you look at the formula how we calculate the asymmetries, we split the diagrams into couplings and kinematics, which means that it is nice to have this identity, these CPT and unity constraints, but you can only use them to check whether your calculation is correct. But you cannot point directly which terms are cancelled by which, because you do not work purely diagrammatically. This will be especially difficult at higher perturbative orders. For example, when you calculate Topikava corrections to CISO type 1 leptogenesis, then there will be like 6 vertices in the diagrams you are cutting, and then it is very difficult to track these cancellations. Also, infinite finiteness is a problem in that case. Okay, so we will first look at something else, and I will show you a model that has irreducible complex couplings that comes with imaginary kinematics in loops, and still we will not get a CP piloting reactions because of the unitarity. So imagine a very simple model of this type. It is it has a discrete Z4 symmetry. So we have some direct fermions psi and some real scalars phi. There are at least 2 of them. And of course, when you fix the phase of this direct psi, then you, for one coupling, then you cannot eat the imaginary phase of the second coupling. So if you have at least 2 such terms in the Lagrangian, then there is irreducible complex phase. Okay, we can have, for example, these loop diagrams for psi psi to psi bar. And there are also T-channel contributions, but for us, these S-channel diagrams are enough. And when we look at the lambda 4 order for the, or lambda 6 when it comes to asymmetry, for the reactions that contribute, we'll find out that there are only 2 possible final states for psi initial state. One is psi bar, and the second one is psi. We assume that the energy is not large enough to produce this on-shell phi. And in that case, of course, the elastic scattering must from CPT symmetry must come with 0 asymmetry. So this psi to psi bar is 0 as well. Okay, so still there must be some other condition to be added to get a CP asymmetric process in theory. And briefly speaking, it is that for a given initial state, you need at least 2 possible final states to be kinematically allowed to get a non-zero asymmetry. Okay, so how to represent this in a more clear and perhaps diagrammatic way, such that we can track the cancellations of the diagrams? And at least at the leading order, it can be done rather straightforwardly. So we use the unity condition in many ways in this seminar. So another way is that we write down T as T dagger plus this term. And we replace in the definition of the asymmetry the first T Fi squared by the expression obtained from the unity condition. And after some manipulations, we will get 2 terms of this form. At the lowest orders, you can cut the corresponding forward scattering diagram only into 3 pieces at the lowest orders. So first, the simplest case comes with the first term only here, which comes with 3 T pieces, 3 Feynman diagrams. Okay, and it can be rewritten as a difference of 2 terms. Okay, so what this means, that I will start with some initial state I, then I will go to F, from F to N, I will sum over all intermediate states N, and then I will end up again in I. So this is a series of 3 Feynman diagrams in a sequence from right to left, and it is a forward scattering diagram cut with 2 on-shell cuts. Now there is no complex conjugation in any of the propagators because we got rid of the dagger here at the lowest order. And then I will have a similar diagram, a similar forward scattering diagram in which the states are in a reversed order. So if there is a diagram contributing to the first term, then the second diagram can be constructed from the first one by looking at the diagram in the mirror and reversing the arrows. And the reversal of the arrows will make a complex conjugation of the couplings. So clearly, there must be an irreducible complex phase in couplings, even from this formula. Okay, this is equivalent to what has been known from the work of Rue, Covey, and Vissani. This is one of the early leptogenesis papers on cis-autamon leptogenesis, and they were looking whether it is possible to have a leptogenesis just from scatterings. And they realized that it is not, because so when you do not produce on-shell heavy neutrinos here, then from the unitary constraints and their notation, the cyclic diagrams are equivalent to this our formula, that just because of the reason that you do not have enough final states for a given initial state, the unitarity will kill the asymmetry. And for this reason, you cannot have leptogenesis just from scatterings. In the simplest model, of course, there are models of leptogenesis based on scatterings, but not in cis-autamon. Okay. Okay. So how to generalize this easy formula, which was working only for lowest order contributions to the asymmetry. When I say lowest orders, I do not mean 3-level contributions, because of course you need higher orders for getting the imaginary kinematics, but at lowest possible. So that means that 3-level and 1-loop level. So beyond this, we can use unitarity, and we can completely forget the imaginary parts and kinematics, and we can use only with the unitary condition only. So I will write it as the IT dagger equal to IT minus this quadratic term, and then I will write down the square, and I will replace iteratively each IT dagger with this equation 16, and I will get possibly infinite, but it is always truncated at some order, because when you are working with, let's say, 6 vertices, then you cannot have more than 6 pieces. Usually you have less because of the kinematics, because you are not allowed to have massless particle decaying and so on. So the kinematics will tell you that you have only 4 pieces, but certainly not more than the number of vertices you have in your calculation. So in a perturbation theory, you will always have a truncated series here. And this is called, okay, this can again be related to imaginary part of the forward scattering diagram. So again, some version of cutting rules, and this was found in 70s and mostly forgotten paper by Koster and Stapp. And then Hofi Hannesdottir and her collaborators wrote a paper where they again introduced this idea by studying the analytic properties of scattering amplitude, and we use it for description of the asymmetries, because when you subtract the 2 squares from I to F and from F to I, computing the CP asymmetry, you will end up in a series of this type, where you have a pairwise, when you sum over all the final states, you will observe a pairwise cancellations between diagrams. So you will exactly be able to point out which diagram and which contribution to the asymmetry is cancelled by the which other one. Okay, so now I will show you an example. So this is the simple Z4 symmetric model, and I'm computing the asymmetry for the psi to psi bar. So this TFI is the first diagram here. Then there is the cut of the loop, which is represented by the integration of the final state momentum. Of course, there is also the summation over the spins. And then TFN is represented by this psi bar to psi contribution, and then kind of elastic scattering here. Okay. When you observe the so-called mirror term here, then you can see that you can take this
I have
first...
a quick, sorry, if I'm not interrupting you, I have a quick question. Is it necessary to assume I, J, and K not equal, or does it matter? Because in principle, if all of them were equal, I could have split the diagram in 2 from the phi J piece and then looked at just that piece itself, no?
if I, j, and k are all equal, then you will have real kinematics, and these two will cancel, but they will cancel anyway.
Yes. Yep. Okay.
They will
see.
cancel
Okay.
anyway, because you have to sum over all the mediators here.
Yeah. Okay.
We are in fact summing over I, j, k.
I see.
Because
okay. All right. Okay. Yeah.
Okay. But
no,
then
go ahead, sir. Sorry,
can...
I didn't want to.
Okay. I will take this forward scheduling diagram, psi to psi, and I can move it to the end of this sequence. Because of the equal kinematics of psi and psi, it will not change the contribution. But in that case, these two terms will cancel each other. And when we look at the second row, the two diagrams are actually equal. There is the reversed order of the k, j, and I indices, but we sum over them because we are not producing on-shell phi. So we have to sum over all the possible contributions, and we have 0, as we expected at this order.
Right.
At higher orders, we will get non-zero contributions, but we will have more psi's in the final state. For example, if we produce psi, and we will get 4 psi's and 2 psi bars in the final state, which will be a bit difficult calculation, then we will have non-zero asymmetries. But in this model, at the lowest order, at which we will expect to get an asymmetry, we will get 0. And each few months, there is a paper on arXiv that misses these cancellations, and people usually forget some contributions, some interferences of terms, and they will get non-zero asymmetries in the models in which the asymmetry is actually 0. So this is an important check to check. You always, when you are computing some mechanism for method generation from the CP asymmetries, you always have to check whether unitary constraints are fulfilled. Okay.
Can you just one quick question? So you said on the second diagram you can move that first part towards the end. Can you explain once more why that's possible?
Okay. So what is here? So this is some some psi1. This is psi2 in terms of initial momentum, and these are the same size.
Yes.
And here we integrate over the four momentum here, of the one over 3 momentum here, and some over spins. And you can do that because you can do that because you will get the
you're
same
also
result
integrating
here.
over. So you're also integrate. Sorry, that's just for me to see. So the T matrix there, it contains also the integral over the final states, right?
Yes. In this way, if it is written with arrow.
Yeah. Oh, okay, and therefore you have both. Okay, that makes sense, because then you can move it. You anyway still integrate over both.
Yes. And this also holds. Okay, I will go to in a few seconds. I will go to Boltzmann equation, and there will be some other things to keep in mind. But okay, so now the summary of the first part. We have Feynman integrals that can develop imaginary kinematics from on-shell intermediate states. This may be from loops, but it may be also from disconnected diagrams or on-shell intermediate states like resonances, which usually is treated in other way, but formally it can still be viewed as imaginary kinematics. There must be irreducible complex phases in couplings. This condition can also be seen diagrammatically, as I will explain. And instead of computing the imaginary kinematics from loops, we can use the unitary condition directly and compute the asymmetries as a product of unconjugated diagrams in sequence. Okay. Maybe if you do not have urgent questions, I can continue, or you can ask now if you have some.
I had, but okay, maybe it's a stupid question. And probably it's a bit naive. So if you go back to your previous set of diagrams,
this one.
Yes. So if phi was extremely heavy, let's assume that each of the phi's were heavy, and I could just integrate them out of the equation. So
exactly.
Then it's basically two blobs, right? So does the sum even make any sense there? Because I can literally rewrite the whole, the whole diagram. I can integrate the phi out of the action or something, and then the blob just becomes a sum of, in the sense that there is psi and there'll be two blobs of psi bar
yes,
each.
yes.
And in that sense, does the difference of the two diagrams make sense? Taking a difference of the two diagrams make any sense?
It will be zero, obviously.
It will be zero, right? That yes. I agree that it will be zero by construction, if that's
yes.
Okay.
It's one way how to see the cancellation in this case. Okay. Yes, but you can still argue that okay, it's okay that asymmetry is vanishing if you integrate out the phi's, but for example, you can still have the case when the asymmetry depends on differences of their masses.
Okay, I see. Okay.
So it's different questions.
I see. Okay. All right. Okay. Thanks. Yep.
Okay. So this I have already said. Okay. So the second and also more interesting part is how this works with kinetic theory. So when it's not enough to have an asymmetry. You need to write down the so-called source term for a lepton or baryon number to get a phenomenologically interesting model. So in general, the Boltzmann equation is the idea that you have some particles moving in the space, and you will count the changes, the processes that change their number. So we have some scattering, some annihilation, some decays, and we calculate the number of these reactions per unit volume per unit time, and we will write down the change of the number density here. This is I guess everyone knows where this comes from. And these gammas are reaction densities. So this is the number of some I to F or F to I. I use the same notation as for the matrix elements. So this is I to F reaction creating some F1 particle and some others from the initial state I. I will sum over all reactions, and this gamma is the number of the reactions per unit volume and unit time, which is represented by this V4 here. So if you know how this T matrix is usually written in terms of the MFI, which is the usual amplitude in the zero temperature quantum field theory, there is a 2 pi cubed and delta 3, and from the square you will get the second power of this 2 pi and delta 3, and this is okay. This should be not cubed, but this should be fourth power and delta 4 actually. Sorry. So this is 2 pi to 4 and delta 4, and there is a 4-dimensional volume which is cancelled here. Okay, there is a short version of the Lorentz invariant measure here for the initial state integrated with some classical phase space density, and for the final states we will integrate also over the 3 momentum, and there is implicit summation over the discrete degrees of freedom. Okay, so for example, for the scatterings, you will have 2 Maxwell-Boltzmann exponentials here, and you can calculate the thermal average, and dividing it by equilibrium densities, you can calculate thermal average via Gelmini and Gondolo paper. Okay, we are going to compute the CP asymmetry, so we need the Boltzmann equation for the asymmetry. So we subtract analogous equation with for antiparticles. So F1 bar, we define the asymmetries in number densities, asymmetries in reactions, and we will get difference of 2 asymmetries on the right hand side. And again, we sum over all reactions that contain F1 particle in the final state. So we are interested in those which create the F1 particle or F1 antiparticle. Okay. In equilibrium, we will, and it is important to say that we do not include at this level the quantum statistical factors, Bose-Einstein enhancement or Pauli blocking. I will comment on that in the last part. We only work with Maxwell-Boltzmann exponentials for each particle in the initial state. In that case, we can take the non-equilibrium part out, so we assume kinetic equilibrium for simplicity. In that case, all the particles can have some anomalous chemical potential, which can be taken out as a ratio of the particle density and its equilibrium value, like this in general for all the initial state particles. Okay, and then we have only the equilibrium reaction rate density. Okay, for the equilibrium phase space densities, we have the detailed balance condition. And if you remember moving the first diagram to the end of the sequence, then if you write down this t squared as a product of 2 pieces, 3 pieces, and so on, thanks to the detailed balance, you can again cyclically permute them in any case. Even if they contain different particles in each state, this does not have to be elastic scattering, for example, because of the detailed balance, because of the sum and integration of the initial state momentum. Of course, if we have equilibrium reaction densities, they have the same property when switching the states. The asymmetry will change the signs. This does not apply to non-equilibrium asymmetries because they may come with different ratios of densities and equilibrium densities. Okay. So when we compute the asymmetry that contributes to the right-hand side, we'll get two terms. One will come, okay, we are working in the lowest order in the asymmetries. So we can have asymmetry either in the reaction density, this delta gamma, or we can come with asymmetries in particle densities like this. And this first term is the contribution to the source term of the asymmetry. So this depends on the asymmetry of the reaction density and actually on the asymmetry of squared amplitude of a process, and only comes with the symmetric part of particle densities. And the second contribution is contributes to the washout terms of the asymmetry, depends on asymmetric densities, and comes with the symmetric part of the reaction. And this typically, in Boltzmann equation, this typically leads to washout of the interaction of the asymmetry. So even if you are in equilibrium, so this is just one, then it can be easily shown in a few slides that you will not develop an asymmetry because of these washout terms. So let us look. We have two terms, one that creates F1 and the asymmetry of that reactions, and one that annihilates F. Okay, so first part first, okay? Then we can see that because of the sum of over all reactions, we must have departure from equilibrium in the initial state. If there is not, we can sum over all the reactions here, and because of the unitary constraint, the source term will vanish. So we only include interactions and processes that produce F. It must be present in the final state, and we need out of equilibrium particles in the initial state. Otherwise, because of unitarity, it will vanish. Then we have asymmetry of processes that annihilate Fs. So we have F1 in the initial state, and we sum over all possible final states. In that case, we will get 0 because of the unitary constraints. We have fixed initial state F in this case, and we sum over all possible final state I. So because of the properties of delta t squared, we will get 0. So the source term of an asymmetry of some F1 particle can be written as a difference of the ratio of initial state densities over the equilibrium densities minus 1. And okay, so we can see that in equilibrium it is actually 0, so the source term vanishes. The washout terms, then I have nothing to say, nothing special. What we only need to keep in mind is the two conditions. Out of equilibrium particles must be in the initial state, and the particle of our interest must be in the final state of the source term reactions. Okay. Now I will include an, I think, interesting example how this works actually. There was an idea. Okay, I could have show you how this works in cis-Taiwan leptogen. Is the most common thing, but then many things will be kind of trivial. So it can be found in many papers, but this is an interesting example how unitarity works in leptogenesis. And the idea of Dirac neutrinos used for leptogenesis was introduced in this paper more than 20 years ago. And the idea is that we have a lepton number conserving decays, lepton number conserving theory, but right-handed neutrinos carrying lepton number will decouple. So universe is lepton and baryon number symmetric, lepton numbers B minus L symmetric, but opposite asymmetry is stored in the right-handed neutrino sector, which is decoupled. Okay, it is known that when we compute the asymmetry, this is the number density asymmetry of right-handed neutrinos divided by entropy density. And it is related to Celeron-induced baryon number by this factor, which is quite common thing known from many years ago, as you can see. Okay, we will, as an example, consider this simple Lagrangian. So we have coupling of right-handed neutrinos and right-handed electrons to some heavy X mediators. There must be at least 2 of them. And then we have coupling of the same X mediators to left-handed lepton doublet. In this case, we have diagrams of this form. We have 3-level decays of X into right-handed electron and right-handed neutrino, the same for left-handed doublets, or left-handed neutrino and left-handed electron. And then we have this type of loop. And from the interference of these 2 terms, we'll get the asymmetries, which will cancel each other. Okay, this is how the cancellation actually look like. We have the contributions to the right-handed final state and the mirror terms that will cancel with the initial terms of the left-handed final state decay. And similarly, these 2 terms cancel each other. So again, we can observe pairwise cancellations. Now, an interesting question. Okay, then there is inverse decay and scattering contributions that the cancellations can be represented in the very same way. The interesting question is whether we can go without the heavy X particles in this case. We should be able, in principle, because we have right-handed neutrinos which are out of equilibrium. We assume that they are at the reheating or soon after the reheating, they have negligible density, and they are freezing in or slowly produced after the reheating. So right-handed neutrinos, these new are out of equilibrium. So this could be, in principle, enough to generate the asymmetry. We have CP violating phases, irreducible complex phases in these F and G matrices in the flavor space. And we have out of equilibrium particles. So the question is whether we can generate the asymmetries. Unfortunately, when we do not have for the inverse decay scattering the final states containing Si, the asymmetry of the right-handed to left-handed state must vanish. And this indeed happened in this paper, unfortunately, but it can be corrected. And the simplest way how to make this idea work is that we change the charges of the X particles and couple them to left-handed quarks. It is kind of leptoquark in this case, scale leptoquark S1, I think. It has the same charge as right-handed down quarks, same charges. Okay, in this case, we have 6 asymmetries. So we have left-handed quarks, leptons, right-handed down quarks, neutrinos, up, and electrons. And because this Lagrangian preserves lepton and baryon number separately, we have these conservation laws. We can express right-handed neutrino symmetry as a sum minus sum of left-handed leptons and right-handed electrons. And also we have each of these terms can lead to some global U1 symmetry. So you can change this lepton and quark doublets, change the phases of these fields in opposite way, so we will get some global symmetry, and the conserved charges will tell you that these 2 asymmetries have to be equal, the same for each of the pair of the fields here. So we have only 2 independent asymmetries, let's say delta L and delta ER. We can write out all the processes exactly as one of you suggested. We integrate the heavy mediators out, and we will get 3 effective vertices of this type, we'll get 3 reactions. So sigma 1 thermal average is the reaction from right-handed neutrino and down quark to left-handed doublet. Similarly, for second and third reaction, we'll compute the thermal averages. All the particles are massless, so that the calculation is trivial. The most difficult part is to take care of the flavor indices in these traces of the coupling matrices. That's the most difficult part. You can compute the thermal averages, and you can observe the simple scaling with reheating temperature and temperature as a temperature of the medium. And we introduce from these traces, we absorb the mass dependence, and we introduce some alpha 1, 2, 3 couplings for each of these reactions. Okay, we calculate the asymmetries, and for now, remember that out of equilibrium particle must be in the initial state. So we look for the asymmetries with right-handed neutrinos in the initial state. And it turned out that the only initial state leading to asymmetry must contain right-handed neutrino and right-handed down quark. 2 possible final states are left-handed doublet and electron and up quark singlet, and we'll get 2 asymmetries equal in size but of opposite sign. Okay? Now, unfortunately, when you look at these 2 asymmetries, they will contribute to the source term of left-handed doublets and right-handed electrons. But the source terms will come with opposite signs. Okay, but that means that we will produce, if this is all we have, we will produce right-handed neutrino asymmetry, right-handed electron asymmetry, left-handed doublet asymmetry, but they will have opposite sign. And because of the lepton number conservation, the right-handed neutrino, the only one that is important for the baryon number generation through sphalerons, will vanish. So we have vanishing source term. Fortunately, this does not mean that we have no working model of leptogenesis because of the difference of the washout terms. Similar idea was introduced for the freeze-out case mostly, but it is a very general paper on freeze-in leptogenesis. Exactly, you have vanishing or not large enough source term, and because of the differences in the washout terms, the asymmetry in the lepton number is washed in. Okay, so we are producing from negligible asymmetry, we have right-handed neutrinos produced via decay, via scatterings from some 2 particle initial state to right-handed neutrino and some other particle. We have some cross-sections contributing in this way. We have reactions from left-handed doublets to right-handed neutrino and down quark, or from right-handed electron and up quark to right-handed neutrino and down quark, and the crossed reactions which will lead to this 5/9 factor. And we have the Boltzmann equations for the asymmetries of left-handed doublets and right-handed electrons. And when you look at the first row in each of these equations, these only differ in sign. So we have plus here and minus here, and these 2 asymmetries in cross sections in thermal averages have different, have opposite sign. But fortunately, because of these second rows, which come with different couplings and different functional dependence on the asymmetries, we can wash in the asymmetry. So how it looks like? So in this first figure, we decided to have all the cross sections, the symmetric cross sections are the same. We have chosen such a ratio of couplings that all the reactions have the same cross sections. The symmetric part of the cross sections is the same, and the asymmetries are tuned in such a way that will reproduce the correct baryon number for our universe here. So we have the freezing of right-handed neutrinos soon after reheating into some non-equilibrium value. We have asymmetry of right-handed electrons, which is of the same size, roughly the same size as the asymmetry of left-handed doublet. And from the small difference, the right-handed neutrino asymmetry, still large enough, even though suppressed, still large enough, is generated. The same for stronger couplings, but in that case, you have a bigger asymmetry at the beginning, and it is partially washed out until the neutrinos decouple. Okay, so the model can work even when you have vanishing source term. Now I will jump to the last part of the talk, and I will go quickly because of the time. The last point of this seminar. Let's come back to the way how we calculate the reaction density in equilibrium. So we have some equilibrium densities here, Maxwell-Boltzmann exponentials, and we have the squared amplitude here. Here should be 1 over V4, not V4, that's a typo. Which reactions contribute? The question. At the low orders, this is trivial, but at high orders, you have to be careful not to forget anything. So systematically, you have to write down all the forward sketching diagrams and cut them in such a way that you will produce all the possible final states, and you will get the sum of the reactions that contribute. So the most trivial case, you have a heavy particle, let's say everything is scalar and the coupling is 1. Heavy particle decaying into some lighter scalars. So the contribution to this T squared is a cut of a self-energy, the imaginary part of the self-energy. And this is the result when coupling is 1. The question, at the same order, you have this forward sketching diagram. Does it contribute or not? It changes the number of, let's say, this thin scalar particle. But when you look carefully, this external leg and this external leg corresponds to the same state. So it is cut twice in this case. And I can rewrite it like this. And the only difference between these two contributions is that for the final state, let's say 1, we have Maxwell-Boltzmann exponential as well. Following this rule that for each initial state, there is a 1 power of density here. We can sum over all possible contributions of this type, and we will get a geometric series, and summing it up, we will get a quantum statistical factor with Bose-Einstein density here. So imagine that you never ever heard about quantum statistics. You start with classical statistics, Maxwell-Boltzmann distributions, and only describe the interactions of particles by means of quantum field theory. And following the rule that you have to include all the forward sketching diagrams and count them, you will get the quantum statistical densities for the initial state as well, because you can sum over all the winding, you can draw the diagram on a cylindrical surface and sum over all the winding numbers of the initial state propagator, and you will get the Bose-Einstein density here instead of the Maxwell-Boltzmann. Okay, so that's nice. How it is related to the asymmetries. So I have to go a bit back. So we started originally with forward sketching diagrams, but how to get all the forward sketching diagrams? The best way is to start at a given perturbative order with vacuum diagrams, or some bubble diagrams, or cyclic diagrams, or whatever. These are used to represent weak basis invariants. So the combinations of couplings in which you may have complex phases and you cannot get rid of them by redefinitions of fields. There is a nice property found by Kovirov and Vissani that when you have such a cyclic or vacuum diagram, it has irreducible complex phase when it is not invariant under reversal of arrows. So the reason why the asymmetry was not generated in this case was that these two diagrams are the same. Here they are not. Okay, usually at the beginning I was cutting the diagram by cutting the sides of the triangles. Now I will cut right-handed neutrino and right-handed electron here, and it may seem hopeless because I cannot cut the loop here, but I can open the quark leg, let's say, and sum over all the winding numbers, and what I will get is the same as if I replace the zero temperature propagator by the thermal one. This you may know from thermal field theory if you have ever seen that. Okay, so now imagine that you are computing the asymmetry in the usual way. So you split the diagrams into kinematics and imaginary kinematics and imaginary couplings. But at finite temperature, to compute imaginary kinematics, you need to modify your cutting rules because the medium changes the onshore part of the propagators. Now you will get it naturally by summing over the winding numbers of the propagators here. Okay, The asymmetric cancellations can be tracked in the very same way. For each of the diagrams with a particular set of winding numbers, you can do the cuts and you can observe the pairwise cancellations as well. What else can be done? Thermal masses can be represented by the so-called anomalous thresholds. CPT and unity constraints, as I mentioned in the previous slide, can be generalized to finite temperature, which has been done for Shiso leptogenesis and Tobyukawa corrections. And it can be also shown that there is no double counting when you proceed in this way. Okay, the basic assumption is that, okay, so far it was only kind of heuristics that let us look how it works. But it can be also derived in a more rigorous way. So we consider each single particle state of the Fock space, described it by means of some density matrix rho in this form, so by means of some occupation numbers of that state, and performing on the all the quantum statistics, taking traces of the density matrix, and the number operators will compute mean occupation numbers of that single particle state, and calculate unitary evolution dividing by V4, and we will get the Boltzmann collision term, and we can derive exactly the rules that you have to start with forward skating diagram and sum over all drawn on a cylindrical surface, and sum over all the winding numbers. So this was, I think, fast, but I think my time is almost over. So if you have any questions, I will be happy to explain more, or you can ask me anytime if you come to these slides, and you can write me an email, and I can explain more details. But the main message is of the second part that you must have vacuum diagrams that are not invariant under the error reversal to come with an irreducible complex phase. And by completing the Boltzmann equation, by all possible unitary cuts, you will get either approximation or full thermal corrections to your Boltzmann equation. And often it will also cure infrared divergences if you have any in the calculation. So thank you for your attention, and I look forward to hear the questions.
Yeah. So yeah, thank you very much, Peter. So we have time for questions. Maybe let me start off here while people are still thinking about questions. So in that model which you considered, so in that second part when you started the one with the leptogenesis, so you looked at 2-to-2 scattering. How about three-body decays? So if you have the stellar neutrino decaying into the three standard model particles.
We assume everything is massless. The right-handed neutrino, it's Dirac neutrino, so it is very very light. There are no decays.
Okay. So there are no decays. So that's just not possible.
Okay, this was just a example model, but you can couple in the very same way. There is a paper by Julian Hick, Jan Hesik, and Anil Thapa, the testing Dirac leptogenesis PRD paper from 2023, and they have table 1 there, and they have a kind of classification of all possible models with on-shell X mediators. But you can integrate the X's out, and you will get all the possible models, all the possible 4-fermion interaction models, and you can do the same calculation as I did in this particle model. So you can get something like Dirac version of the neutron portal in that case, and to do leptogenesis. And not leptogenesis, but directly the baryogenesis.
The baryogenesis, yeah, because you couple to baryons.
Yes. But the calculation will be up to factor of 1. It will be the same as here. So.
Okay, thanks. I have another one to that, so maybe let me just continue there. So you mentioned there that the source terms are vanishing, and so you basically only get it from the wash-out terms, or you get that, yeah. But before starting that, I think at the end you mentioned kind of when you started the whole discussion, you basically said that you need the source term to get the asymmetry.
I didn't. Okay, you need source term for some asymmetries, at least some.
Yeah.
So we have the source terms for electrons and left-handed doublets for L and ER.
Okay, but you don't have it. Okay.
if there are only these two asymmetries, then they are completely washed out by sphalerons. And nothing will survive. So I need some small difference and some small asymmetry to be stored in right-handed neutrinos. And it comes from the difference in size of these two guys. They have opposite sign and some small difference in size.
Okay, okay, so, but then it's mainly coming from those washout terms in the end.
Yes, yes. Because if you write down the Boltzmann equation for delta nu r asymmetry, you will find out that it is 0. It contains only wash-in terms,
yes,
depending on the asymmetries of L and ER.
But you have the source terms for the delta ER and for delta L. That's basically the...
Yes.
Okay, good. Then it makes sense. I got briefly confused there. That's... Yeah. So everyone is too shy to ask questions, but let me ask something about the last part. That's been a little bit too quick then in the end for me, but just to get a basic message. So technically you start just with Maxwell-Boltzmann, right? And you sum over all of those diagrams which wrap around that cylinder. Is that, and from that you get the quantum statistics. So it's similar to what when you derive in statistical mechanics the
Exactly. And in the proof that can be found in the last section of this paper, we actually work. You can even see it here. So this is very similar to equilibrium case. That you have this FP which parameterizes the dependence on occupation number, the rho p dependence.
Yeah.
And you compute this normalization factor. You have some analog of the Maxwell-Boltzmann exponential here. You can define some analog of classical densities, and then everything is very similar to equilibrium case. When we look first at this winding number, for us the most important point was when we realized that we get correct result for thermal corrections to seesaw time on leptogenesis, because there was some non-trivial aspects, and up to that time the only correct calculation was within the closed time path formalism by Lindner and Garbrecht and Kartelzer and this group. And we somehow miraculously got the correct thermal corrected source term. And then we started to look whether this is just a miracle of equilibrium densities, because it looks like you can always expand the Fermi-Dirac or Bose-Einstein in terms of geometric series, and it will look like this.
Yeah.
But it turned out that the essential part is not having equilibrium and Maxwell-Boltzmann, but single particle states. You cannot have multi-particle correlations. So the density matrix must have this form.
That you always have just single particle, you grade and annihilate a single particle.
Yes. And I make product of the single particle state density matrices for all the Fock space.
Okay. So that's where it's related to. Okay, that's interesting. That I didn't realize. That I didn't. Yeah. I don't know. Please, sorry, I interrupted you.
I only wanted to add that when you look at this propagator, you know that in thermal field theory or closed time path formalism, you have propagators that are 2 times 2 matrices.
Yes. Yeah.
Here it is not the case, because we get rid of the dagger in T squared. We do not have complex conjugation there.
Okay, wait, but in the... Let me see. So we basically don't have the anti-Feynman propagator in those.
Yes. So when you imagine the closed time path, it goes from some initial time to some other time and back, and then minus e beta. But when you can stretch the contour from minus infinity to infinity when going to Boltzmann equation. And in that case, we do not need the lower part of the contour.
Okay, because so you can really use that in-out formalism instead of that in formalism. But that's only because you take that Boltzmann limit. So when you go to the
yes. So this kind of top-down, bottom-up approach to quantum kinetic theory instead of the top-down usually people do.
Okay, That's interesting. Yeah, I have to read your paper there on that. That's yeah. We looked at some other ones and tried to basically use it. So in comparison to the normal cutting where you have the T and T star, or T and T dagger. Yeah.
If there are any questions even later, then write me email and I will be happy to help.
Yeah, thanks. That's good. So are there any other questions? If not, then I would say we close the official part of the seminar. So yeah, thanks a lot, Peter, or Peter.